Hello, my name is Kristina Zvolanek, and I am presenting a hands-on tutorial to map cerebrovascular reactivity as part of the OHBM educational course on physiologic fMRI signals. I have no financial relationships to disclose, but I am a member of the PhysioPi community, which is a group of researchers aiming to help collect, share, and analyze physiological data interfacing with MRI. I will be presenting software tools developed by the PhysioPi community in this video. Other talks in this course have introduced cerebrovascular reactivity, or CVR, and described it as a metric of the brain's vascular health. Kevin Murphy introduced how you can utilize simultaneous recordings of physiologic signals, like end-tidal CO2, alongside an fMRI acquisition to estimate CVR. Pei-Ying Liu described how you can extract CVR from the bold signal itself without external recordings. And Molly Bright described a modification to resting state fMRI that allows you to measure both CVR and neural activity. Please see these videos for more details. The goal for my talk is to give a hands-on introduction to just one analysis method for obtaining CVR maps, called the lag-GLM method. After a brief introduction, we will transition to installing and running code with an example dataset to prepare the physiologic input data and generate CVR maps. Then we will visualize and discuss the outputs. As a brief reminder, CVR describes the brain's blood flow response to a vasoactive stimulus. We can map both the amplitude, or how big the blood flow changes, and the delay, or how long that change in blood flow takes. Here are example CVR amplitude and delay maps in an individual with unilateral moyamoya disease. You can see the difference in CVR delay between hemispheres, whereas CVR amplitude is consistent. The dynamics of the CVR response vary throughout the brain, even in healthy individuals, so accounting for this delay improves the accuracy of our CVR measurements and gives us a separate insight to vascular health. There are many different ways to acquire CVR, but in general it requires a vasoactive stimulus combined with a neuroimaging method to measure the blood flow response. See the review articles at the bottom of the screen for more details. In this tutorial, we will use data where the vasoactive stimulus was a breath hold task. Breath holds increase the pressure of CO2 in the blood, and you can see in this figure the increase in CO2 following the breath hold. This increase in CO2 causes the blood vessels to dilate and increases cerebral blood flow. As a result, there's an increase in the bold response to reflect this change in blood flow. There are also several strategies to analyze the bold fMRI response to measure CVR. Please see the previously cited review articles and other talks in this course for more details. The most common approach uses a general linear model framework to build a model of the bold response, similar to what is done for task fMRI. In this case, we have the bold time series for a given voxel as our dependent variable, and we model this time series with a regressor of interest to explain our task, and nuisance regressors such as motion or drift. Then we estimate the amplitude of each of these regressors, and we have associated error terms with these estimates. Several different signals can be used as the regressor of interest to model the breath hold task. In this tutorial, our regressor of interest is end-tidal CO2, the pressure of CO2 at the end of an exhale, measured in units of millimeters of mercury. End-tidal CO2 is a close approximation of the CO2 pressure in the blood. It also allows us to quantify physiological changes during the breath hold and account for variations in task performance. End-tidal CO2 is measured via a nasal cannula that samples the air from each exhale, connected to a gas analyzer which samples the concentrations of CO2 in each breath. The advantage of using CO2 is that the beta coefficient for this regressor in the general linear model represents CVR amplitude. You can see the units here. So we have our dependent variable percent bold, our regressor of interest, CO2, is in millimeters of mercury. Therefore, our beta coefficient is in units of percent bold per millimeters of mercury. And this is CVR amplitude units, the change in blood flow response per unit change in the vasoactive stimulus, in this case, CO2. And the advantage of this is that it gives us CVR in normalized units, which allows us to make comparisons between subjects. To obtain CVR delay measurements, we need something a little bit more sophisticated than the standard general linear model. And we call this the lagged general linear model, or the lagged GLM approach. This involves creating shifted versions of the task regressor, so end-tidal CO2 in this case, and then iteratively running the general linear model with each one. So first, we make multiple shifted versions of the end-tidal CO2 trace. And then we perform the GLM for each shifted version of this regressor in each voxel of the brain. Then for each voxel, we find the shift that best explains the bold signal by giving the maximum full model R squared. And this shift in seconds represents the CVR delay. So we can make CVR delay maps based on these optimal shifts, as shown in this figure. And lastly, we can use the shifted end-tidal CO2 regressor to then make lag-optimized CVR amplitude maps by extracting the end-tidal CO2 beta coefficient at this optimal shift. Several software packages are publicly available to facilitate modeling of CVR amplitude and delay and related metrics with different variations in their modeling approaches. These include CVR by Alex Bogle, Quantifies by the University of Oxford, and the Bold CVR portion specifically by Joanna Pinto and Martin Craig, Rapid Tide by Blaise Frederick, and fizz2CVR by Stefano Moya. In this tutorial, we will use the lagged GLM implemented by the Python-based software fizz2CVR. The analysis steps to run the lagged GLM involve first pre-processing the fMRI data using standard pre-processing techniques, and then preparing the end-tidal CO2 reference signal. This involves first extracting the end-tidal peaks from the CO2 trace, then convolving this end-tidal CO2 time series with the hemodynamic response function. Next, it's important to temporally align this end-tidal CO2 regressor with the average gray matter bold time series. And this is to account for any measurement delays or general vascular transit delays. And then from this temporally aligned or reference end-tidal CO2 time series, you create shifted versions to run the lagged GLM. And these shifted versions can be in a specified increment within a certain search range. And then lastly, you use these shifted regressors to run the lagged GLM. In this tutorial, we will start with fMRI data that has already been pre-processed. However, we will use raw physiological data, which means we need to prepare the end-tidal CO2 reference signal. We'll use a software called PeakDet to identify the end-tidal peaks, and then the other software we'll use, called fizz2CVR, performs the remaining steps automatically. And then we will run the lagged GLM with fizz2CVR, and finally, we will talk through the key outputs and view them in FSLIs. The data that will be used in this tutorial can be downloaded from the Open Science Framework at this link, and the folder that it's in is listed as well. The data has been saved in BIDS format, as Mary Miedema demonstrates in her tutorial for this course. Our sample dataset is from one healthy adult participant on a 3T MRI. They completed 8 cycles of a breath hold task, while CO2 was recorded with a nasal cannula, and an fMRI scan was acquired. See the README file in the folder for more details, and the information below about the Excalibur dataset, where this comes from, and the paper describing the acquisition and analysis methods. Before we start the tutorial, I want to give a disclaimer that the content shown here may be different on the day of the educational course. The analysis steps are dependent on the code versions that are available at the time of this recording in July 2023. I understand you may face difficulties with installation on your operating system, and I would recommend referring to the documentation for each software package, but I'm also happy to try to answer your questions as I can. And for the in-person educational course, we hope to offer a virtual environment that will allow everyone to participate. To follow along with the coding portion of this tutorial, you will need to install Git or GitHub Desktop, and you will also need a working version of Python, version 3.6 or greater. I also suggest having a text editor, a Python integrated development environment, and FSLIs to view some of these CVR maps. The software to install includes PeakDet and Phys2CVR, and the links to these GitHub repositories are shown here. I will demonstrate how to install them in the next steps. And lastly, there are example scripts for how to use these software programs on my GitHub profile at the link shown here. And now let's get that software installed and start mapping CVR. The first thing we will do is install the 2 necessary software packages. So I have gone to the GitHub repository for Phys2CVR, and there are instructions on how to install if you scroll down the page. So you can install with Python using pip, or you can clone from GitHub and install it without using pip. I will show the method for installing with pip. So you should be able to just open a terminal window and use this command shown here to install Phys2CVR. I already have the version installed, so I won't actually execute this command, but it should be relatively quick to do this. Next, let's install PeakDet. So to do that, you do actually need Git integration. So here is the GitHub repository for PeakDet, and there is a read the docs page on the side, which has more detailed information. So I am going to go to this website and the installation and setup page, and I will follow these instructions again in the terminal. So since this involves cloning a GitHub repository, it will create a local folder on your computer. So you first want to make sure that you are in a directory where you want to store this code. So for example, if I want to store this in my documents directory, I will need to change to that directory via the terminal. And now, once I am there, I can type these or copy and paste these commands. So first, I will clone this repository using this command. So I just copied that and pasted that into the terminal here. And now I clicked enter. Now that folder has been copied to my computer. So if I list the contents of my documents, there are several folders, but you can see here that we have a folder called peak-det. And now we want to change into this directory, as the command on this website says. So we want to change directory to peak-det, which now, if we list the contents, has all of the code and documentation that we need. And so now that we are in this directory, we can use this command to actually install peak-det. So I will copy and paste that into my terminal. And again, I won't execute this command because I have already installed peak-det on my system. But once you do that, you should have everything that you need to use peak-det within Python. So now that we have our software installed, let's also download the data that we're planning to use. So if we go to the Open Science Framework link that is listed in the tutorial video, or you can just use the address here, it will bring you to this page, which is where the PhysioPy community stores some public data. And if you scroll down on the page, there is a tutorial folder for this course. If you click the plus to expand that, there is another folder with the sample data. So you can expand that to see the contents. And then if you click download as zip, the contents should download. So you can download those and unzip them to have all the files locally. Then one last setup item is to clone or download the code that I have prepared for the tutorial. So if you go to this repository on my GitHub profile, the link is, or the address is shown here, and the link is provided in the tutorial as well. We have some scripts that will be useful for this tutorial. So you can clone this to your local computer, or you can also just download as a zip file if you prefer. Or if you are using GitHub Desktop, you can also open it with that. I will show how you can clone it to your desktop. So what I am doing is I'm going to open a new terminal window, and then I will use the command. Actually, first, you want to make sure that you are in the directory where you want to clone this code. So again, I'm going to change directory into my documents folder, which is where I want to clone this. And then I'm going to just use the command git clone. And I will copy the link to this repository here, paste it after this command, and press enter. And now all the contents have copied. I am going to now save the sample data within this folder. So if I just navigate to my documents, this is the code that I have just copied in there. And then I'm going to open a new window here to access the downloads of my sample data. unzip that and then copy it over to this folder. So now I have the sample data downloaded, all the code, the software installed, and I am ready to start actually processing the data. Okay, so now we are ready to prepare our CO2 file. And to do that, we will use this Python script, prep CO2. And I'm going to open that in Spider, which is my Python development environment. And this includes all of the commands that you need in order to process the CO2 trace. I just want to point out that you can do this from the terminal. So if I open a new terminal window and run Python with IPython, I can just copy and paste these line by line and run that there. So in case that works better for you, you can do that, but I will be showing how to do it in Spider. So I am first going to import these modules that we need. And then importantly, you should change the path to where the sample data you downloaded is. So I know that mine is in this directory, but it is in the sample data folder within that. So I'm going to run that. Check that my path has been loaded. And then now we're going to import the physiological data from that TSV file. So I ran that line, and now we're going to specifically extract the CO2 data, which is in the 5th column, or 4 if you use Python indexing, which starts at 0. So let's run that, and then we will plot that to see what it looks like. So you can see here, if we expand this window, that we have CO2, and we can see each of these sinusoids here is a breath, and then we have a breath hold here when there is a drop in CO2 because the person is not breathing, and then after the breath hold, we see an increase in CO2 due to the breath hold. So I will close that plot. And now we need to change the scale of CO2 from volts to millimeters of mercury. And this conversion factor is from this citation here. So we will run that to rescale it. And then now is when we start using PeakDet. So we have loaded it or imported it as a module as PK, and we're going to load our CO2 data into the PeakDet object, which is a physio object. So we tell it the data that we want to go in and the sampling rate, which is 40 Hertz. So if we run that line, now it's in the format that PeakDet is looking for in order to automatically extract the peaks and then to review them manually. So in order to automatically detect the peaks, we run this operation within PeakDet called peak find physio. And we input the variable that we want to use, which we've already defined in the previous line. And then these threshold and distance variables can be adjusted in order to improve the automatic peak detection process. So we will run this line, and then we will see that the automatic detection does a pretty good job, but we actually want to manually review and edit those peaks to be sure that we captured true end tidal peaks. So I'm going to execute this line, which is calling on the operation edit physio. And this opens an interactive GUI that will allow us to review peaks. So first, let's just review what a good end tidal CO2 peak looks like. So I just zoomed in there, and now I'm going to just scroll through. And this here is a pretty good example. So this is our CO2 trace during a breath. And so this is the exhale portion, and that end tidal value is the peak at the end of that exhale. So we're looking for a very clear plateau shape, and that is what we decide as a good end tidal value. So we're going to go through and double check that the peaks have been found where we want them to. So these traces are not ideal, but that's about as good as we're going to get there. That one is pretty good. Also pretty good. So it's looking good. And also want to point out, so this algorithm identifies peaks in red and then troughs in green, and they are always in pairs, but you can only edit the peaks at the moment, which is fine because that's all we need for end tidal CO2. So I'm just going to zoom out a bit. Oops. So here is an example. Actually, I'm not going to do that at the moment. So we will go back to our scrolling. So this is the first breath hold. You can see that there's a decrease in the CO2 values here, but we are getting peaks in here, which we don't want. So in order to remove those, you can toggle off this pan, and then you can right click over and drag over the peak to remove it, and it removes the associated trough. So I'm going to remove that one, this one, this one. Essentially, we don't want any peaks within the breath hold period because we only want to capture that change from before the breath hold to after. So I removed that one as well. And now this is the peak after the breath hold, and it looks fabulous. It was higher than the values before and looks like that plateau shape. So I'm going to keep scrolling through here. Oops. And so I'm going to keep scrolling through here. And here is an example of a peak we want to remove. So it's just a little, probably short breath in between proper exhales. And it's a sinusoidal shape, so it doesn't look like a proper end tidal. So we will remove that. And now we have gotten to the second breath hold. So again, we've the algorithm has identified some peaks in here that we don't want to include. So I'm going to right click and drag over and remove them. And keep scrolling through here. And this looks okay. It's not great, but it is our best estimate of that end tidal CO2 after the breath hold. So we'll keep it. That one looks okay. That one looks okay. Again, this one is not ideal. It's not that perfect plateau, but it's not horrible, so we'll keep it as our best guess. And then coming up on the next breath hold here, we'll remove these peaks in there. And remove these all at once. And this is our peak after the breath hold, which looks good. And this is a pretty ideal CO2 trace right here. It's pretty easy to tell where the end tidal peaks are, and they've done the breath hold very well, and also performed the exhale at the end of the breath hold, which is what we need in order to get those estimates of end tidal CO2 at the end. And that is where some participants struggle at this place specifically. They either forget to do this exhale or don't do it with the right pressure, so it's not recorded with the nasal cannula. So this is a good looking trace to show you what the ideal scenario is. Okay, so we're to the breath hold again. We'll remove these peaks. These peaks. And then this value after looks okay. That's good. So you should be able to do this on your own, but you can refer back to this video for references on what was added and removed. We'll take out that one again because it's very sinusoidal, doesn't have that plateau shape we're looking for. Now into a breath hold period. We'll remove these peaks. That one looks okay. The end is probably about here, but these are very similar values. These look good. That one I will keep, and then to the next hold those. Keep that peak after the breath hold. We should be getting close to the end of the scan here. These are, we don't want to include that one again. That's sinusoidal. And it's now in a breath hold period as well. So we don't want to include these. That peak looks okay. This one looks okay. Also notice I zoom in this far just to see each breath very clearly, and I like to see the trough and the peak. So the algorithm did good here, not including that one. But we will remove this one. Okay, so now we are done manually editing the peaks. We can just close this window and it will save the indices that we have identified. And now we want to save the array of indices where those peaks happen in our CO2 trace as a separate file. So first we need to export, set them to a new variable. So we've saved those peaks in this object. So we will run this line, and then this is the file name we want to use, and then we'll save it in that folder with our sample data. And oh, it looks like those lines didn't run because I didn't quit this GUI. So now we have saved our file, which tells us where in the CO2 trace are our end tidal peaks. You can also export the indices of the troughs if you want to, but we don't need to for end tidal CO2. And then we also want to demean our CO2 trace, which is important when we run the lagged general linear model. We want all of our regressors to be demeaned. So we are subtracting the mean from our CO2 time series there, giving it this file name, and then saving it as a text file to that folder. And then we're also going to just save the physio object that we created in case we ever want to reload it and manually edit the peaks again in the future. So again, just giving it this file name and saving out that file. And then this here is an example of how you could reload the peaks and check them if you wanted to, or use them for any other analysis purpose. Okay, so now we have finished preparing our CO2. So as a review, what we've done is we've extracted the peaks in our CO2 trace where the end tidal values are, and also demeaned the actual CO2 trace. And both of these will be inputs to phys2CVR, which runs the lagged general linear model. So next, we will run phys2CVR. So we can close this now. And to run phys2CVR, there are two different ways you can do it. So now that it's been installed, you can just directly call it from a terminal. So if I type phys2CVR, for example, it will output the help information. So this lists all of the different input options, and you can see actually if we type phys2CVR-H, it will give a more detailed description of what all of those inputs are, starting here, and it will tell you also which arguments are required and which are optional. So you could run this command directly from here if you want, but to make it easier for our purposes and also to show how you could script using this command, we will use a text editor to describe the inputs and then actually run that script from the terminal. So if we go back to our code that we have downloaded, we will open this run phys2CVR shell script. And I will run that, open that in my Sublime text. So again, the first things to edit are the directories where you want to save, where you want to input data from, and then where you want to save data to. So the input directory is the same, except it has an extra A that we'll remove. Let me see, save that change. And then the output directory is going to be in the same folder I've been using, but with the name phys to CVR outputs. So here I have listed the file names and set the variables of all of the different inputs to phys to CVR. So we'll just go one by one through them. So the first option is your input file, and that is your pre-processed bold fMRI nifty file. So in our sample data folder, we have this file, which is described as a breath hold task and our bold native space pre-processed. So that's our input file. Then the next input down here is our output directory. So we've already defined where we want to save the outputs. And the next option is to run phys to CVR within a mask. So we have given it the option of using a brain mask. And up here, I've defined the file name for that brain mask, which is given in your sample data folder. So it's just a brain mask in native space. And this helps us because it speeds up the lagged GLM, because it tells phys to CVR to only run that model within the voxels that are in the brain, rather than within all of the voxels in the entire image. The next input is our gray matter mask. So again, this is in your sample data folder with the name GM native. And that is the ROI for phys to CVR. So, and you can see it here, that is the -R option. And what that does is tells phys to CVR where we want to take an average time series when we are finding our first optimal shift with our end-tidal CO2 regressor. So if you remember from earlier in the video, one of our first steps of the model is to temporally align that end-tidal CO2 regressor with the average gray matter bold time series. And so this is what tells phys to CVR to create a gray matter time series. The next input is TR, which is defined here, and it's 1.5 seconds. And that is for our fMRI data. Then we input the CO2 file. So we have created that and just exported that from our Python script. And we remember that we have demeaned that. And then we also need the file indicating the indices of the peaks in that previous CO2 file. So we also just created this file and exported it from Python. And so these two inputs are shown here. And this is going to tell phys to CVR how to convolve the hemodynamic response function with our CO2, our end-tidal CO2 trace, so that we can get that final input regressor. Next, we input the frequency of the physiological data or CO2 recording, and that's 40 hertz in this case. And then in our model, we want to include Legendre polynomials to model scanner drift. And so you can tell, you can specify which degree of polynomial you want to include. And so we have used 4 based on the length of our scan. And that is this option here, LDEG. Next, you can specify your nuisance regressors to include in the linear model. So we are including just 6 motion regressors. And those, again, have been included in the sample data file. And they are indicated by this MCF suffix. And again, note that they are demeaned. And if you would like to include more nuisance regressors, for example, the motion derivatives, you could just enter, add another variable after this DMAT option. Next, we want to use a scale factor, and this just converts the data from bold to percent bold, so that we can get our CVR in units that are comparable to what's used in the literature. Then you tell phys2CVR what to set as your lag max. So this is the range of CO2 shifts that we're going to consider, from -9 to +9. And this value has been chosen and justified in the literature as the range that compromises or that contains the delay values for most healthy adults. So if you are using a different population, for example, a population with pathology, you may want to reconsider this lag max. And then our lag step is the increments at which those end-tidal CO2 regressors are created. So this is saying that we will create a shifted CO2 regressor at 0.3 second increments from 0 up to 9 and from 0 to -9. And then we'll run the linear model on all of those shifts. So in total, we're going to have 60 regressors plus that 0 shift, so 61 total models. So I'm happy to answer any questions you have about these inputs, and also please see that help of phys2CVR for more details. But now that we have set up this script, you can just run it in the terminal to actually run phys2CVR. So if we first change into the directory where that script is located, and for me it's on my desktop here, let's just list the contents to see, and we do see that run phys2CVR shell script, and it's an executable script. So we can just run it by doing / and then the name of the script and press enter, and it will start running phys2CVR for us. So it's also giving us helpful outputs to tell us what it's doing. It's currently running it. It's telling us it's using this input file, running or using the average signal in gray matter, finding the cross correlation between that gray matter time series and end-tidal CO2, and the delay between them is 19 seconds. And now here we can see it's performing the lag GLM, iteration 1 of 61. So we will wait for it to run and then check back in. So now our phys2CVR is done running, and we want to go through the key outputs. So first, let's check the folder that they saved in. So in our tutorial folder, we saved them in phys2CVR outputs. And you can see here, we have several file outputs. In the tutorial video, I have listed a summary of the outputs, what each file name contains for your reference, and we're only going to go through a few key ones in the interest of time. So first, we'll take a look at our end-tidal CO2 regressor that has been convolved with the HRF and optimally aligned with the bold time series. So that is this PET CO2 HRF image. So if we open that, we can see in blue the end-tidal CO2 trace involved with the HRF, And then in orange is the average gray matter bold time series, and you can see how well they align here. So this is our zero shift CO2, which is then used to create the shifted versions. You also have in this text file the actual regressor downsampled to the TR. And in this file, you can actually see an image of our original CO2 trace in blue, and then in orange is where the end-tidal peaks are. So this orange time series is our end-tidal CO2 trace. But the exciting stuff is the CVR and lag maps. Actually, one more thing before we get to that is this folder contains the regressors. So all of those shifted variations of our end-tidal CO2 are contained in this folder as text files. But now to the exciting stuff. So we have a CVR_simple, which is our CVR map without the lag GLM. So when we just use that optimally shifted end-tidal CO2 regressor, only one model for each voxel. Our CVR file is our actually lag optimized CVR. So within every voxel, we're using the end-tidal CO2 time series that has optimized our model. Then we have the lag map or the delay map, which tells us within each voxel how many seconds was that CO2 regressor shifted to optimize our model. But what we really are interested in is this lag_mkrel file, which is the delay map or lag map that is relative to the gray matter median. In other words, the delay in each voxel was subtracted by the median delay in gray matter, which helps us normalize the map for each person and make comparisons between people. So let's look at these outputs in FSLIs. So first, we will actually just look at our lag optimized CVR map. So I will open that in FSLIs. You could also open this in AFNI or another image viewer of your choice. So first, we want to set the color bar and the scale. So I normally use the red to yellow as the positive color bar, and then we want to indicate that we want a negative color bar, and then we can actually toggle on the color bar to specify that. And the reason for this color bar is that we want to see the distinction between positive CVR and negative CVR because they represent different phenomena. So, and then we'll change the scale here. CVR is typically, this map is in units of percent bold per millimeter mercury. And those values in a healthy adult are usually between 0 and 1. So now, once we set that range, you can see the CVR map. And what you should immediately see is the gray matter ribbon. That is one indication of a good CVR map. So if we scroll to some different slices here, let me point out just what I mean. So these yellow spots, for example, are gray matter, and we see higher CVR in gray matter because there is a higher vascular density there and we have higher signal. So this is looking good from that standpoint. And then another thing that you should see on a CVR map is big draining veins. So if we look at this sagittal slice here, you can see this huge yellow blob all along the superior portion, and that is the sagittal sinus. So that is a big draining vein, and we are sensitive to the bolt signal there. And there's a big change in the signal there due to our breath hold task. You can also see another draining vein here. If you go through different sagittal slices, you should be able to see them as well. So that is looking good. Something else to point out is that we do typically see negative white matter in negative CVR in the white matter and ventricles. And those mechanisms are slightly different than the arterial dilation that causes the CVR effects in gray matter. And there are several papers about this, so I encourage you to look at those, but just want to point out that it's a normal physiological feature of the maps. So this is a great CVR map, and this would be how to check your output and see that it's reasonable. You can also, in the window down here, check the actual value within each voxel. And we typically, again, want to see values in the range of -1 to 1, sometimes a bit above that. So now let's look at our lag map. So if we import it from that folder of our outputs, we will look at the lag MKREL map again, because that's our map that's been normalized to the gray matter median. And again, we will change the color scale here. And the color scale that I normally use and that some people I collaborate with use is a Viridis scale, but inverted. So these color bars can be imported to FSL, and I will include those files in the GitHub repository. So for the negative color bar, for the positive color bar, we actually want to use the negative range of Viridis, and then the opposite for the negative. And we want to select this option so that we have a negative to positive range. And the reason we use this inverted color scale is because we want to see delays that are earlier in yellow and delays that are later in purple. So let's first set the range here to 5 and orient you again to the color scale. So 0 seconds is actually the median delay in gray matter, because this map is made relative to that value. So a 5-second delay in this map indicates that the CO2, the response to that CO2 change happens 5 seconds later than it does in gray matter. Whereas a -5 or a yellow indicates that that response happens about 5 seconds earlier. So lag maps, you can tell it's pretty speckly. They are noisy, especially on the subject level. That's normal. It does get better if you smooth the data first before running the GLM, or once you start looking at a group level in MNI space or with group averages. But some key features to note are that you should see values in gray matter that are around 0. So this like turquoise to light blue color. That should be primarily the gray matter voxels, because that is, again, what our reference was, and those should all be near 0. So if we scroll through here, we do see that for the most part. And then another key feature to look for is that the delay in the posterior portion of the brain, and especially the cerebellum, should be later. So that is well seen here. For example, this dark purple indicates that later response time, whereas structures like the putamen should have a much earlier arrival time. And then another check is that white matter should also be later, especially relative to gray matter. The delay there should be later. So we should see, as we do here, like some purples throughout there in the white matter. So this is the basics, the quick rundown on CVR mapping with the lag GLM and the outputs. There's more outputs to sift through, and I'm happy to. As I mentioned, here is the summary of Phys to CVR outputs, since we didn't have a chance to go through all of them. I'd like to acknowledge my lab at Northwestern University, led by Molly Bright, and our collaborators in Spain, especially Cesar and Stefano Moya, who is the brains behind most of this code, particularly Phys to CVR, and who has done an amazing job organizing this course and the PhysioPy community. My funding sources, and then the entire PhysioPy community and all of the contributors to the code we've used. And then again, here's links and citations for the code repositories, and then the Excalibur dataset, which Stefano Moya also provided. And with that, thank you for listening. Please reach out to me with any questions you have. My email is listed there, and join us for the in-person course at OHBM. Details listed there.